Our calc students, here are with trig functions integration, which integration is always a little trickier. So part of our basic trig integration rules is just take the derivative rules and take them in reverse. So remember how the derivative of the sine was the cosine? So the integral of the cosine is the sine. And if the derivative of the cosine is negative sine, the integral of the sine is negative cosine. And so forth. The integral of secant squared would be tangent. Secant u tangent u would be secant u. So, and the derivative of the secant tangent would be secant, or integral. Integral of cosecant squared would be negative cotangent u. Integral of cosecant cotangent would be negative cosecant. Now, don't try and memorize all these. It's getting to be a huge list now. So if you're going to be the person doing this on your group test, have these integration formulas on the go. So for 2 cosine x, the constant multiplier rule says we just move the 2 out. And the integral of the cosine is the sine. Don't forget your constant of integration. Notice here with sine x cubed, you got 3x squared outside. Conveniently, the 3x squared is the derivative of the inner function. So you can use a u substitution there to get a negative cosine of x squared. Same with secant. Integral of secant squared is tangent. We get this 3x. So we actually have to create a 3 inside, compensate with a 1/3 outside. Okay, now what are we going to do with this one, tan squared? Well, this is where you use a trig identity to simplify it so you can do some of the things that we've got available. Tan is equal to secant squared minus 1. Secant squared x minus 1. That's one of the Pythagorean trig identities. So you get the integral of the secant squared of x dx minus the integral of dx. So you just get tan. Remember how the derivative of the tangent is secant squared, so the integral of secant squared is tan. Tan x minus x plus your constant of integration. Okay, and let's do our TI-89 check. See what the TI-89 says. Integral tan x. Now you got to make sure you got the integral symbol. You can put the tan x in parentheses and square that, comma, with respect to x. Let's see how the calculator does. Now the calculator did something real trippy here. It gave me negative x cosine x minus the sine of x all over cosine x. Put it all into cosine. If you divide this through, you get negative x cosine x over cosine x. Minus minus makes plus sine x over cosine x. And that sine x over cosine x is tangent. And notice how this multiplies the negative x. This is one case where I really would not accept the calculator answer. That's so much more complicated than our simpler answer like this. Plus, remember, the calculator forgets to put the plus c when it does an integral. Okay, let's look at our next one. Cosecant x plus sine x times cosecant x. Well, none of these fit any of our antiderivative rules, but if we distribute and say cosecant squared of x plus sine x times cosecant x dx, integral of cosecant squared of x dx, plus this simplifies down to just 1. So this cosecant, that's the integral of cotangent. So it's negative cotangent of x plus the constant of integration. Let's see if the T89 does a little better on this one. Okay, and so here's what the calculator came up with. Negative quantity 2 cosine x minus 2x minus pi sine x all over 2 sine x. Well, it's equivalent. You can see the cosine over sine making a cotangent, and it keeps it negative. And also the negative cancel, we get sine over sine, that cancels, and we get 2x over x, that makes it an x. But what is this pi thing doing in here? Well, that's going to just be a constant. That's part of what could be in here. So I'd say this is equivalent. Equivalent, but not simplified. Not when we got something like this over here. So this time I'm only going to accept this answer, and I'm not going to accept that. So integration by use substitution now. This is where it gets a little tricky here. Integral of secant squared of x over square root of x dx. So you equal the square root of x. So then you have u equals du is 1 over 2 square root of x dx. So 2 du equals 1 over square root of x dx. And so you see how you can change this now to the integral of secant squared of u, and then this 1 over square root of x dx, all of this then can become your du. So in essence then you get the tangent of u plus your constant of integration, and then unsubstitute tangent of u, which is square root of x plus c. There you go. Now here's one involving the power rule. Because sine squared of 3x equals the sine of 3x quantity squared, you can let u equal sine 3x. So that becomes our inner function, the sine 3x. And the derivative of du, if u is sine 3x, its derivative is cosine 3x times 3 dx. So what we're going to need here is du over 3 equals cosine 3x dx. So we can replace all of this with du over 3. And the sine squared of 3x becomes the sine squared of, it basically becomes u, sine squared of 3x is sine of 3x quantity squared, and sine 3x is our u, so that's how that part becomes u squared. So it's 1/3 u squared du. So it's 1/3 u to the third over 3 plus the constant of integration. So u cubed over 9 plus the constant of integration. Unsubstituting now, u is sine of 3x, so it's a sine of 3x cubed over 9 plus c. And there you go. That could also be written as sine cubed of 3x over 9 plus c. Let's see how the TI-89 does on this one. It did a great job. First, be careful in entering your integral. Left parentheses, and then left parentheses sine, left parentheses 3x, right parentheses. And we want to take all of this and raise it to the 2. Then times cosine 3x with respect to x. And it actually says sine 3x, all that quantity cubed over 9. Don't forget, though, to add the constant of integration. So I'd accept it like this or like this. All right, more problems. Substitution in the power rule. Okay, let's figure out what you use for u on each of these, and then you can look at how the book did these out here. The trick is to look for the inner function. What do you suppose the inner function is here on a? Sure enough, yeah, this thing inside the powering here, the cosine underneath here. So you've got u in this case. In part A, we're going to use u equals cosine x. So then du will equal negative sine x dx. And very handily there, you've got a sine x dx right there. Here in part B, it looks like we want to have u be the inner function, in this case cosine 4x. So then du is 4 sine 4x dx, because that inner 4x function and derivative of cosine is negative sine. For part C, the function inside the square root there is the tangent, so u equal the tangent x. And then du equals secant squared x dx. So notice how we went to the inside of the chain of functions, and sort of ignoring the other one for a while, and it turns out to be the derivative of what we need. So look at this first example, sine x over cosine x. There's our u, which we pick as, remember, u equals cosine x here, and that becomes u to the negative 2. And then negative sine x dx then is our du. And there you have it. And you end up with secant x plus c. Here in this case, remember we said our u is going to be the cosine of 4x. So du is, the derivative of the cosine is negative sine. And don't forget the derivative of the inner function there, so you get 4 dx. So we need to create a negative 4 sine 4x here, and so that's why we had to put a negative out here. This 4 here was handy, but we also needed another negative. So you end up with a negative cosine 4x quantity cubed over 3. plus your constant integration. Here, remember, u was going to be tan x. So du is secant squared x dx. And conveniently, there's a secant squared x dx right there already in the integrand. So it becomes u to the negative a half, and now you can use your power rule to get that. Now, the antiderivative of the tangent. We think of the tangent as sine over cosine, and now we can actually use our log tricks to come up with a very strange answer for this antiderivative of negative natural log of cosine x plus c. Some people even write this differently. They put the negative one inside, and they say the natural log of absolute value of cosine x raised to the negative 1 plus c. So natural log of secant x plus c, absolute value. I'll accept either one of those. And here's the integral of the secant, even more complicated. You have to multiply by just the right thing so that you get rid of the top in there. Now, what motivates you to multiply by secant x plus tan x or secant x plus tan x? Hindsight, who knows? So that's where we get a bizarre rule for that one. So here's your list of rules for all 6 trig functions now. Sine, cosine, tangent, cotangent, secant, and cosecant. And notice the ones behind the sine and cosine, which were so nicely sort of derivatives and integrals of each other with a few negatives. These become much trickier and involve the natural logs. So keep those in mind when we're doing this one now. So integrating the square root of 1 plus tangent squared dx. And this time we're going to do some a definite integral from 0 to pi over 4. Well, 1 plus tangent squared is secant squared, so it's a good idea to actually simplify what you've got inside here first. So we get the integral from 0 to pi over 4 of the square root of 1 plus tangent squared is secant squared dx. And the square root of secant squared is secant, so 0 to pi over 4 of the absolute value of secant x. But in this range it's always positive, so we'll just go with secant x dx. Now the secant, that's one of these tricky ones over here. We've got to go natural log of the absolute value of secant x plus tan x plus our constant integration, but we're doing a definite integral now, so we're just going to go from 0 to pi over 4. So it becomes the natural log of the secant of pi over 4 plus tangent pi over 4 minus the natural log of the secant of 0 plus the tangent of 0. Secant of pi over 4, let's use our unit circle here. At pi over 4, the cosine is 1 over square root of 2, so the secant is square root of 2, so it's a natural log of the square root of 2. Tan pi over 4 is 1. Minus the natural log of the secant of 0, the cosine at 0, the cosine is 1, so the secant's 1. Plus the tangent of 0, which is 1. Now natural log of 1 is 0, so we end up with just the natural log of 1 plus the square root of 2 for our exact answer. Let's try our TI-89 check. Remember doing definite integrals? You just have to add another argument on here. Left parentheses again, or we go right to square root, left parentheses 1 plus tan x. You're going to have to get all that raised to the 1.5 power with respect to x, going from 0 to pi divided by 4. Let's see how our 89 does on this. Okay, we came up with one mistake here. Careful with this now, gang. That's raised to the 2, not the 0.2. Raised to the 2. And the calculator gave me the natural log of 2 square root of 2 plus 3 all over 2 for the exact answer. They both calculated to 0.881375, and a lot of this just has to do with how you're approaching it. So there you go. And we're refer exercises. Okay. Flange out.